What's up, you guys? Yes, welcome back to another PY212 review video. I'm Seven.
I'm Roger.
And I'm Mark.
And today we're going to be covering Faraday and Lenz's law. Don't forget Lenz's law, guys. Let's go! Okay, guys, we're going to be talking about Faraday's law real quick, right? I feel like people think this is confusing, but it can all really be boiled down into one very simple statement. Or simple might be a stretch, but it can be boiled down into one statement that really sums up the essence of Faraday and Lenz's law, really. If the magnetic field through a closed conducting loop is changing over time, then there will be an induced EMF and an induced current, right? Okay, that sounds great and all. What does that actually mean? So, okay, the first thing that you would probably think about after hearing that statement is, okay, changing magnetic flux will create a current, will create an EMF, but what exactly causes the flux to change, right? So if we remember our little equation over here, right, where our magnetic flux is equal to the integral of B dot dA, right? So what would actually cause this value to change, right? Well, the first one would be if the magnetic field was changing over time, right? Like, let's say it was increasing, let's say it was decreasing, right? That would change the magnetic flux, right? What else would change the magnetic flux? Well, it would change if the area was changing. If the area inside the conducting loop was changing over time, then that would also change the magnetic flux, right? And now the last thing is, since this is a dot product, right, the angle between the two matters, right? So if the angle between the magnetic field and the area vector are changing, well, then that's also going to change the magnetic flux, right? Okay, cool. Those are the three things that will change the magnetic flux. So we've gone over what that is qualitatively, right? But here is actual Faraday's law written out, right? Where the EMF in that system that we were talking about is going to be equal to the negative derivative of the magnetic flux with respect to time. Easy money, right? Easy money. This only tells us about the EMF, but where did the EMF come from? Like, what is actually going on over there, right? Well, like I said before, right, there's going to be an induced current in the loop, right? And the EMF is actually just the work done to make the current move through the system, right? That's where the EMF comes from, right? So now let's think a little bit more about the current that's going to be induced. If we know that there is a current induced from the magnetic field, right? Well, what else does that tell us about the system? Well, let's recall Biot-Savart and Ampere's law, right? Where we learned that currents create their own magnetic field, right? Which is kind of wild to think about, right? There's an external magnetic field, and as that induces a current, that induced current creates its own induced magnetic field in addition to the external one, which is pretty sick. So that's where Lenz's law comes in, right? Where Lenz's law is saying that the induced current goes in the direction so that its magnetic field opposes the change in the external magnetic flux, right? And that sounds kind of confusing because there's a lot of moving pieces, right? But we're going to look at some examples to kind of wrap our heads around that. So another way of thinking about Lenz's law in kind of more layman speak, I guess, is Lenz's law is just the stubborn law, I guess, right? Where the magnetic flux is changing, right? But then because of Lenz's law, this system's like, I don't like that we're changing. I don't like that we're changing. I'm going to try and induce a magnetic field so that things kind of look like how they were before, right? So let's take this enclosed loop right here, right? So this is a wire over here. And let's say there's a magnetic field pointing into the page within this loop. And let's say that magnetic field is increasing, right? So if the magnitude of the magnetic field is increasing into the page, right? Basically what's happening is that this loop is incredibly upset that it's increasing and will induce a magnetic field to decrease the magnetic flux, try and make it decrease, right? So that means if there's more going into the page, the loop will try and create a magnetic field out of the page to compensate for that, right? So that means it's going to be inducing a magnetic field out of the page just like that. It's not going to fully compensate for it, but it sure as hell is going to try, right? And so from this, we can say, Okay, well, if the induced magnetic field is coming out of the page, which way does the current have to be going in order to create that, right? So that's when we're going to get our good old right hand back out, right? So we'll point our thumb in the direction of the induced magnetic field, right? The induced magnetic field is pointing out of the page, and then our fingers are curling in the direction of the current that is causing that, right? So in this case, our thumb is pointing out, so that means our current is going counterclockwise. So yeah, that's kind of one case of Lenz's law. And let's look at a slightly different case, but equally as valuable. Now let's look at this system. Now this system looks very similar to the other one that we just covered. Main difference being that the magnitude of the magnetic field is actually decreasing as we're as time goes on, right? So the magnetic field, it's still going into the page, but the magnitude of it is decreasing, right? Well, let's think back to what Lenz's law says, right? Lenz's law is like, oh shoot, this is decreasing into the page. Well, I have to then induce a magnetic field into the page to try and keep it the way things were, right? So we know that the induced magnetic field has to also be going into the page, right? Super sick, super cool. Now let's figure out what that means for the current, right? So once again, we'll use our right hand again. Take our thumb, we'll point it in the direction of the induced magnetic field, bah! And then our fingers are pointing in the direction of the current that induces that magnetic field. So in this case, this is going to be going clockwise. That's the way things go. So our current is going this way. Key thing to remember, right? The magnetic field that is induced by the current, right, opposes the change in the magnetic flux. So that does not always mean that it opposes the direction of the magnetic field. It always opposes the change in magnetic flux. That's a key distinction that is very good to know. And I'll leave that for you to marinate on as Mark talks about the next problem.
Okay, guys. So we're going to look at problem 3 from discussion 9, which is a problem about two solenoids, one surrounding the other. And so if we look at our inner solenoid, we can look at it from either the side, like this, or we can look at it sort of from the beginning, from the left here, going to the right. And so we can see that in each case we have a current flowing through our coil, and this current produces a magnetic field, which is into the board, if we're looking at the solenoid from this perspective, or it's from left to right if we identify the points where the current is going through the board in our solenoid. So we kind of slice this picture here so that we can see inside what the B field looks like. And so what's happening in this problem is that this current I, its value is changing in time. We have an increasing current with time. And so the magnetic field inside the solenoid, its magnitude is given by this expression. So mu naught is a constant, and so the physics is contained in this Ni over L. So N over L tells us how densely packed are our coils. So N, right, if we have more coils per length, then they're more densely packed and we get a bigger B field. I is the current flowing through the coil, and we should expect that a higher current through the coil gives us a higher B field. Okay, and so this B field is changing because the current is changing. Now, if we consider our outer solenoid, right, I've just been looking at one, but if we take this picture here and we draw in our outer solenoid in blue here, since this B field inside the green loop is changing, there is a changing magnetic flux through the blue loop. Magnetic flux is a flow of our B field through a surface. In this case, our surface is the area enclosed by our blue loop. So it's a circle, right? So our area is just going to be pi r squared. And normally you would have to consider a dot product here. You may have seen B vector dot A vector, but we are taking advantage of the fact that our B field is perfectly normal to our area, to our surface, which is the whiteboard, essentially. Okay, and so there's a changing magnetic flux through our blue loop, and this should set off some bells in our head about Faraday's law. A changing magnetic flux induces a voltage or EMF in our wire. And so that's what Faraday's law tells us. And for each loop that we have of wire, we induce a voltage which is proportional, or rather equal to the change in time of magnetic flux. And so if we keep adding coils, which is what we do in a solenoid, we pick up an extra voltage change with each loop. And so the more loops we have in our outer solenoid, the larger the induced voltage. And so that's why this thing is proportional to N. Okay, and now we're in a position where we can say that the EMF in the outer coil is given by the number of coils on the outer solenoid times the area. And here we have to be careful because earlier I said the area is of the outer loop because we're looking at the flux through the outer loop. But that's not quite the case because the B field only exists inside the green loop. Outside of the green loop, there is no B field. And so there's no changing B field, there's no changing flux. And so actually when we say A, what we're referring to is the area of the green circle. And with that, we have our number of coils times our area times the change in time of our B field, which, looking at this expression, mu naught n over L do not change in time. They are constants. And I is where we get our changing magnetic field. And so putting these things together and taking the numbers, the values that are provided, making sure to keep everything in SI units, right? So we're given radius in centimeters. Make sure you convert that to meters, etc. We obtain a value for the induced EMF when the outer coil has 120 loops, and we get 6.4 millivolts for that, right? And volts is the right unit here. This epsilon is a voltage, which, right, that's why we get a current, right? When we have a voltage across our wire, that wire has some sort of resistance, and then through Ohm's law we get our induced current, which I have labeled here. Now, in part B of this problem, we're asked to determine what happens to the EMF when we change the number of coils. And like I said earlier, with each coil, you pick up the same d phi b dt amount of voltage. So the more coils you add on the outside, the larger that induced EMF. So when we have the number of coils, we also have the induced EMF because the two are proportional. So we get 3.2 millivolts when there is 60 coils. In part C, we're asked about what happens if we make the outer coil larger, meaning the radius increases. And so this is going back to the question of what A refers to in this problem. So in general, right, for the flux, we care about the entire area enclosed by our wire loop. But since only part of that area has a changing magnetic field, we actually only care about the area in green. And so even if we make the blue circle larger, the green circle will still be inside the blue circle, and nothing will change about the induced EMF. And so that's problem 3 for you guys. Hopefully that was helpful. And always think about these sorts of pictures, right? It's always useful to draw these sorts of things from a few different perspectives, because anything with magnetic fields is happening in 3 dimensions, and it can get difficult to imagine everything at once. So hopefully that made sense. There we go.